and share my screen. Okay, and I have the 4 problems loaded up into Python tutor right here, and we're going to go through them one by one. And again, just double check, make sure that I copied all these problems correctly over into Python tutor as we go over them. The first problem here is related to building up a list instead of taking a list down. And so the way the problem is getting smaller or closer to our end is the closer to our base case is that the length up here is getting closer to this bigger number instead of closer to 0. Walking through this, going in here, and we're starting off our initial list right here that we're passing into our first function call, our initial XS, has 4 elements inside of it. So we're not starting off at an empty list. So we're not going to run this maybe the full time, but at some shortened number of times. And each time we go through this, we're going to be appending 1 to the end of this list over here. So this is modifying a list. So it's also a little bit testing your memory management knowledge as well as the recursion knowledge. But each time we're getting the list bigger by 1. And so we're going to run through this list or run through this recursion, keep doing these recursive calls down here until the length of the list gets up to 10. So just press next a bunch of times. The length of the list is getting bigger and bigger. And then each time we, so now we're at 10 up here in our list. We're going to come down and actually, oops, I guess one more since we have to be greater than 10, not equal to 10. Oops. What am I doing? If the list of the length of XS is greater than 10, yes, the length of the list is greater than 10. It's at 11 because the last index over here is 10. And so we are at this point getting into our recursive call. And every time we do this, we'll start off with 2. The very first one of these will be replaced by 2 here, and then we'll be multiplying that by 2 each time, once for each of these recursive calls. So when I press next right here, we'll see that it says return 2 down here at the bottom. That will be substituted in for the 2 right here, and we'll get a 2 times 2. Not all fitting on the same screen, but there we go, is our return value of 4. Press next times 2 to 8, and keep pressing next, multiplying by 2 each time until we get our last value of 256, a very famous power of 2 because this is the largest number that can fit in a single byte of data. So 256 is your final answer. If you wrote that, you get 2 points. If you wrote anything else, then you get 0 points. No partial credit here. Yes. Say it again. If you wrote 2 to the power of 8, then yes, you can still get credit on this quiz only. In the future, it has to match exactly. Problem number 2. Here, the key idea about problem number 2 is that as we start running through it here, you can see that we're checking our base case, coming down here, making our problem smaller and smaller with each recursive call. Eventually, we get to an empty list down here, but you'll notice that the length of the list right here at this position, when we execute line 2 right here, the length of this list is equal to 0. It is not less than 0, so we're not going inside of our return 0 right here. We'll skip over that and never actually trigger the base case because the length of a list can never get to be less than 0. And so this is going to recurse forever and get the infinite recursion. And so the correct answer is printing out stack overflow. If you wrote that out, you get 2 points. Anything else is 0. Any questions about this problem? Number 3. This is very similar to the recursion problem number 3 that we had on the last quiz, just subtle differences about the math that's going on down here. And the fact that when we first run this go function right here, it's no longer 0, 0 that we're initializing it with. We're just initializing it with these arbitrary values that I just picked out of thin air, 1 and 2. And so there's just a lot of things to be careful about down here. We're building up our accumulator with these two different math formulas, multiplying by excess at position I. The very first I is again the 1. We'll never consider this 0 position up here, the 1. There's the 2 value. So accumulator times 2 gives us 4 right here. And then the accumulator minus equals 1 down to 3. And if you keep doing all the math, step through it all those times, you get 11 as your final answer. Again, put 11, you get 2 points. Anything else, 0 points. Any questions about this problem? Number 4. We have our multiple recursion going on here now with a larger list like I promised you before. And the operations up here are a little bit different because we're subtracting once and then adding on another time. So sometimes you'll be subtracting, sometimes you'll be adding. The key difficulty about the multiple recursion while you're working through it on pencil and paper or in your head is keeping track of when you're in your call stack, if you press next a bunch of times here, when you're in your call stack here, which this foo function right here, it got called from this foo function right here, the call stack, the function at the bottom is always called from the function immediately above it. But there's multiple locations that it can be called from, and you have to keep track of which one of those locations you were calling from. And so there's just a little bit of extra bookkeeping that you have to do in order to do that. When you were working through this problem, you might have noticed that these lists or these subproblems over here, there's only like 5 different possibilities of what these subproblems can be because the original list only has 5 elements in it. And so there's only 5 possible slices that you'll be taking. And so you're actually repeating some of these function calls with the same values over and over again. Python has to reevaluate those each time. But if you noticed that, oh, here's foo with just the number 5 passed in as a list, and that happens multiple times, you didn't have to repeat that work manually. But Python by itself would have had to repeat that work. There's a programming technique called dynamic programming or memoization that if you go on to take CS 148, the graph algorithms class, you'll spend a lot of time talking about, is how to make computer programs not have to repeat the work on subproblems that they've already computed at one point. But I'm not going to step through all of these things. If you ended up getting -6 as your final answer, then you get full credit, 2 points. Any other number right here, you get 0 points. Any questions about any of these problems? Okay, yeah, I went over the answers extra quick today because we got a lot of things to talk about. If you do have questions about any of them, happy to talk about them after class. But go ahead and total up your points. Again, the quiz is out of 8 points, each problem worth 2 points, and then pass those quizzes up to me. Yes, value for the third problem was 11. Okay. Last time in class, we started talking about the idea of classes, and we covered all the material that you'll need for the quiz a week from today, next Wednesday. Again, the file that we went over is this quizpractice.pdf. I think there's still some more copies over on the podium over there. Today, we're going to review some of that. I'll go really quickly through these lecture notes up here in the README file. And then we're going to jump over to the terminal where we left off last time. We were talking about this file yield_examples.py. And so again, if you want to follow along with what we're doing in 5 minutes or so when we get to this spot, make sure that your GitHub repo is up to date, running the git pull command, and then you'll be able to step through with what we're doing here. Anytime you see the class keyword, so again, class is letting you define your own data structures in Python. And using classes, programming that uses classes, or programmers that use classes are doing what's called object-oriented programming. That an object is the name for what the class keyword is creating. Object-oriented programming, often abbreviated as OOP. And one of the, I don't know, shibboleths of somebody who has not been a programmer for a long period of time is that they pronounce this as OOP. So if you're pronouncing this as OOP to other people, you say that, oh, I do OOP programming, or I learned about OOP today, then they will know that you're not a real programmer, that you haven't been programming for a long period of time. People will either say OOP or just actually say object-oriented programming. And again, our motivation for looking at classes is going to be thinking about all of these classes as containers somehow. And compared to other, I don't know, data structures, curricula, we're introducing this class keyword relatively late, sort of midway through the semester. I personally think that object-oriented programming is very much an overdone concept, and the other styles of programming are more useful in practice. I have just some quick pictures over here of the left-hand side of these pictures is all standard, like justifications, classic justifications for object-oriented programming. But then the right-hand side, once like people are making lots of classes, things end up getting really ugly. And so it's not, I don't know, the advertisement is that object-oriented program makes code super simple, but usually it still ends up being very complicated in practice. This man over here, Edward Dijkstra, is a very famous computer scientist. He's invented something called Dijkstra's algorithm, which is what we're going to be sort of ending our course with, going over Dijkstra's algorithm. It's the classic algorithm that all data structures classes everywhere end in. And when we use it, we'll actually be using it to make an AI for the Risk board game using this Dijkstra algorithm that he created. But he agrees with me. He says, object-oriented programming is an exceptionally bad idea, which could only have originated in California. And there's been this sort of split historically in computer science between Californians and everybody else. And in particular, when we think about California for computer science, we think about like Berkeley and Stanford back in the 50s, just immediately post World War II. They, out of researchers there, created this sort of object-oriented programming style, which is in contrast to things called like the functional programming style, which came out of MIT and those more Boston research-oriented areas. Dijkstra worked in Texas, so he was in the middle. He sided with the people on the East Coast. The textbook, again, starts off at the very beginning with classes in chapters 1 and 2. So if you want a textbook reference for what we're talking about this week, start with this right here. This realpython.com, though, is a more detailed reference going into all of the like nitty gritty details, this is a more higher level reference up here. We've talked a little bit about the different vocabulary objects already. So again, an object is the thing that a variable references. All the things over on the right-hand side over here are objects. All of the things on the left-hand side under the frames down here, these are the variables. The names are the variables. The thing that the arrow points to is the object. And an instance of a class is just an object whose type is that class. So this is an instance of the list class right here. Every object is an instance of some class. Again, I'm never going to ask you to define any of these terms. I'm just going to start using all of these terms and expect that you'll be able to keep up with me and follow along with what we're talking about. Python is famous for, in its object-oriented programming, doing something called duck typing, and we'll see a little bit more about how that's going to work when we switch over to the terminal. But the basic idea of duck typing is that we never care about actually what the type of a class is. In other programming languages, especially if you maybe did like AP Computer Science, or if you've seen Java or C++, they care a lot about the type of classes or instances. What class is an instance, is an object an instance of? In Python, we never ask that question. We only care about what are the functions or attributes available as part of that class. Again, anything to the right of a dot is an attribute. Object-oriented programmers, so we're going to be seeing some two new examples of classes today that are sort of built in to Python, and object-oriented programmers thinking a lot about how they structure these classes. We've seen so far this dunder method. Again, anything that starts with these double underscores, we call them dunder methods, short for double underscore methods, or magic methods. The init dunder method is the constructor of our class, gets called whenever we first create the class object. And then we've seen this repr function as well, REPR standing for representation, which pretty prints our objects. And that takes us up to everything that we've seen so far. And now we're going to move on to new things here. I'm going to switch over to our terminal. And again, it's this yield_examples.py file that we'll be going over. I have my terminal split into two sessions like normal, but I'm doing this vertical side-by-side split so that we can see more code at once. And again, you should really make sure you're in the habit of pressing tab when you're completing your file names. Much, much faster, avoids typos. And so I've opened up my yield examples file over here on the left-hand side. And on the right-hand side, I'm still in the same working directory. We'll start with a Python 3-i yield examples. Let's move this thing out of the way. And we can run our code here on the right-hand side. We're in the interactive Python. I know that because the prompt is the 3 greater than signs. Again, I use the -i up here for interactive mode to load up my Python file so that I now have access to things like this factorial function right here. And I can run something like that. And we get the corresponding values shown down here in the doc test. Last time we walked through the first 3 of these functions in this file here. I'm gonna do that again using some little Vim magic right here to move our cursor around a little bit faster. A very useful Vim shortcut that I type all the time in Python. I'm just gonna type it on the right-hand side over here so that you can see, are these double square brackets like this. This will move you forward and backwards between Python definitions. So this one right here, this is sort of like, with the way that I think about it, is this is like a forward arrow, similar to how this would be like a right arrow here. If you change the greater than signs to square brackets, it's like a right arrow going right. So that tells me that I'm going to the right. And then the other one's going to the left, lets me quickly move between all of my different functions here. And we talked about this factorial function, which just computes the factorial, and it's a reasonably efficient algorithm for doing that, the theta of n. And then we started talking about the all factorials 1 function right here, which not just a single not just a single value, but all of the values it's computing. It has this inefficient implementation because internally it's calling this factorial function. So even though this looks like it's a linear runtime, it's actually a quadratic runtime. And we had this special term of accidentally quadratic for these things that look linear, but are actually quadratic. And accidentally quadratic runtimes turn out to be a major problem in programming. If you're doing technical interviews at Facebook, Microsoft, Google, or wherever you're doing technical interviews at, one of the reasons they focus so much on your understanding of computational complexity and runtime analysis is because something like this will bring down a web service. And again, this link right here has dozens and dozens of examples of major web pages or major products that have gone down because somebody did something like this. It looked like it was linear, but it was actually quadratic. And so we were talking about how do we fix things like this, make it both look and be linear runtime. And that was the next function that we talked about. I'll press ZZ to center that right here. This all factorials 2 function. And again, what the all factorials 2 function did is it sort of took the factorial function and inserted it into the all factorials 1, kind of what we call inlining the function, just copying and pasting the function down in here. And now we only have a for loop right here. There is no function call, so this is still going to be linear time right here. But the key thing about this is that we're building up this list. And so we're going to be storing all of the intermediate results from our all factorials function. The runtime is still linear, but now we say that the memory usage of this function is also linear. The memory usage is the amount of memory that we have to use to run this function. So here it's the size of this list right here. The size of this list is going to be, it'll have length in at the end of running this function because if we put in a 3 right here, our in value, the output will have 3 items in it, all of the factorials from 1 up to 3. So this function right here, we say that it has computational complexity of theta in, and it also has memory complexity of theta of in. The previous functions, this one up here, it's building up a list. So this also has the memory complexity of theta of in. And this one up here, it's not building up a list at all. The only variable we have is this integer right here. So this one would have a memory complexity of theta of 1. I mentioned before that there's a handful of, traps that people fall into when they're thinking about this asymptotic notation and algorithm analysis. One of those common traps is that they only think about computational complexity as the only thing that this big O notation can be used for. But there are many other properties of programs, dozens of properties of programs that people care about. And memory complexity is a very important one, how much memory your program uses. And we still use the same big O notation to talk about that. I've come down here again to the all factorials 2 function. You might say, okay, well, the computational complexity, that's really the thing that we care about because we care about how long our program is going to take to run. Maybe we don't care about memory complexity too much. But what we're going to do next is see what is the actual problem that results from having a large memory complexity. Under this note right here, you'll see there's this little command right here that if I run the all factorials 2 function with a small number like 10, it works just fine, gives me my 10 numbers that are these factorials. But if I use a really large number, I don't even know how many zeros are here, but it's a big one, like that, then what's going to happen is you'll get this memory error that the program can't even print out the very first of the factorial numbers because it tries to compute all of them, and there's just not enough memory on the Lambda server in order to do that. So caring about the memory of an algorithm ends up being just as important as caring about the computational complexity of the algorithm. And so this again brings us up to where we finished last time in these notes, and we wanted to think about how can we fix this problem? How could we have a function that gives me back all of these factorials, but does not take up so much memory? And our key idea here is that usually, or maybe not usually, but very, very often, when we are wanting to return a collection of things, one of the things that we want to do with that collection is loop over that collection with a for loop. And so as an example, I'm going to just write a for loop right here. Something like for I in all factorials to 10, and then print I equals I like this. I'm going to take away these vim numbers over here so that I can copy and paste this command right here over into my Python interactive. When I have a multi-line thing in interactive Python, anytime you have a colon at the end of the line, it lets you print out, or it lets you type in the subsequent lines, and you'll have these dot dot dots down here to indicate that this is a follow-on line from the previous one. I'll hit enter right here. You'll notice it still gives me the dot dot dot. It knows to run this, all of these previous lines together. It runs them as soon as it has a totally empty line right here. So I'm just going to press enter right now without running anything, without typing anything, and it will run all of these things for me. The key idea here is that looping over the output of a function is an extremely common pattern. And we've seen many functions where you've only ever put it inside of a for loop. Things like the range function, very common to do something like for I in range, or the enumerate function, something like for I comma x in enumerate of something. Very common to have functions inside of for loops, and we want these functions to not have to allocate more memory than they need to. We want them to be able to actually not allocate any memory at all, so that we can have a for loop like this that can loop over a very large number of items, maybe even this many items up here, without crashing and still be able to work. So that's our objective, what we're trying to accomplish right now. We're going to introduce two new concepts in order to do that. The first of those concepts is called a generator, and it uses this yield keyword down here. Any function in Python that uses the yield keyword inside of it is a generator. So the yield and generators is synonyms for each other. Yield implies function is a generator, and function is a generator implies it uses yield somewhere. And if you look at this code, what it's doing is it's the exact same thing as our original factorial function. In order to demonstrate that, I'm going to demonstrate another Vim feature here real quick. In most editors, you would only be able to open up a file once at a time. I'm going to actually open up this same file side by side inside of Vim. So do :tab E. In another tab, I will open up this same file, yieldexamples.py. And so now you notice that I have two tabs here, both to the yieldexamples.py. And up here on the right-hand tab, I'm now at the factorial function. Here's what it looks like. And I can switch between these two tabs just to switch between locations in the file. So down here on the bottom is on the left-hand side, my all factorials 3. And then over here on the right is my factorial n. I'll just line those up so that we can switch back and forth. And you can see as I switch that, the code for these two functions right here, these lines down here, the code for these functions looks extremely similar to each other. The key thing here is this yield result down here. Intuitively, what yield is doing is that it first returns the results, but then instead of leaving the function, it's going to come back into the function after the yield statement. So return, when you see return, you leave a function and you never come back. when you see yield, you leave a function, and then you will come back into this function later, and you'll come back right after this yield statement. In this case, that's the end of this for loop, so we'll go into the next iteration of this for loop. That's the intuition behind the yield statement, is that you'll come back into this function and then repeat that same work over and over again. In order to actually understand how that works, we'll have to do what's called desugaring this yield statement. This yield statement is syntactic sugar for a type of class and some magic methods, some dunder functions. And so we'll desugar this, see exactly what's going on, and then hopefully that will make the intuition up here make a little bit more sense. Before going into that desugaring thing, now's a good time for us to pause for questions. If anybody has questions about anything that we've talked about so far, or maybe big picture questions about where we're going. Yes. Question is yield the same thing as print? And the answer is no, they are very, very different things. Yeah, exactly what they are. So print, if you print something right here, the function that called you does not get access to that value. If you return something right here, the function that you call does get access to that value. If you yield something, the function does get access to that value. So this is still going to give that value out to whatever our previous calling function is. On the right-hand side, in order to demonstrate that, notice that this is all factorials 2 up here that we're looking at. All factorials 3 is what has the yield function right here. And all factorials 2 on the right-hand side is what I previously wrote down here. I'm going to rerun that line from above, now with all factorials 3. And you'll see that it still is able to get all of this information, that it's all factorials 3. We call the function right here, and it's yielding those things one at a time to this for loop, so putting them in this I variable here one at a time, and then printing them out down here. If you see a function with a yield, if you see a generator, it's probably the sort of function that you want to have inside of a for loop after the end statement over here. And conversely, if you're using a for loop and you see a function over here to the right of an end statement, you probably want that function to be a generator. Yeah, if you're feeling a little bit like, I don't know, confused about the details of exactly what this yield thing is doing, that's a 100% okay place to be. At this point, the goal is to get the motivation for the yield, some of the situations where it might make sense to use that. And what we're going to talk about next year is actually the code that is equivalent to this, the code that this is syntactic sugar for. And as we're going over that code, it'll make it clear exactly what this yield statement is doing. So this function right here, all factorials 3, because it uses the yield, because it's a generator, it is syntactic sugar for a combination of 2 classes that work together. And at the very bottom of this yield examples file, you see this class factorial, and then there's another class factorial iter right here. I was using the square brackets right here to jump between the class definitions. The square brackets, so the right, left, like this jumps to the next top level definition. This is a top level definition because it is indented all the way to the left. If I want to actually go to the next function or previous function, so go up to this line right here instead of the class definition up here, the way to do that is by putting an m to the right-hand side of the square brackets. Square bracket m like this takes you to the left definition, next definition. Square bracket m, right square bracket m takes you to the right definition. So we're going to talk about these classes, what they're doing, and then we'll tie them back into the yield and generators in a minute. There's quite a bit of things going on in these classes, so it'll take us a little bit before we can see exactly how this relates to the generator. You can see, though, just from the doc the doc tests down here that this is in fact generating the same sort of results down here. And on the right-hand side over here, if I come back up to my for loop and change this all factorials 3 to factorial to the name of the class right here, the name of the class right here, change it to that, and rerun this same loop, we'll still get the same output. So this class right here is 100% equivalent to the yield generator that we have above. You can see there's a lot more stuff going on here, so that'll make it easier to understand, easier to step through what's going on at a detailed level. But once you get comfortable with this idea of generators, you won't want to have to be writing out all of this code when you could just write a 3-line function like we have up here. Okay, so in order to figure out what's going on with this class, we'll just go through it one function at a time. We've already talked about the constructor function, the init dunder method or magic method, and this is what gets called when I do factorial. So if I do something like x equals factorial of 10 like this right here just called the constructor over here. I can verify that by inspecting the value of the in attribute of this x variable. To do that, I do x dot in. Again, the thing to the left of a dot must be an object somehow. So this x was created, the object that is referenced by x was created by the factorial function over here, by the constructor of the factorial class over here. So this is an object to the left of the dot, and then to the right of the dot is an attribute inside of this variable. I know this attribute will exist because down here we have the self.in right here, which actually creates the attribute in all of the instances of this class. On the right-hand side, I'll hit enter, and you can see that it has the 10 down here for x.in. I'm going to go through this entire class not using Python tutor at all, just doing things inside of the terminal to see what is the equivalent terminal things that get you the same information as Python tutor. If after today's lecture, though, things are still a little bit fuzzy, the thing to do would be to try to repeat what I'm doing right here, repeat all of these steps in Python tutor so that you can get the actual visual representation of what's going on. But the thing I'm going to do next, the thing that's different than something that we did in Python tutor is how can I get what are the list of attributes for a particular object. And there's a special built-in function dir in Python, which tells you the list of all of the attributes of the object. dir of x, I hit enter, and you can see there's a big list of things down here. You'll notice that most of these things are magic methods, dunder methods. They have these double underscores all over the place. And by default, when you create a class, Python creates many dunder methods for you automatically. At the very end down here, you'll see this right here. This is the actual attribute over here that was created on this line right here. So any attribute that you create that doesn't have the dunder methods inside of it will appear at the end, and it'll just be the name, same exact name of the variable as over here. You'll see that we have an init function. We created an init function. You can find init right here in this list of all of the attributes. And then we also created this repr and this iter function. We could find those over here somewhere. Again, the repr function is going to be how do we display this any instance of this class, and the x variable refers to an instance of this class. So if I type x right here and hit enter, this right here called the repr function, and the repr function returned this thing right here, which is the same as this right here. In general, your repr functions, what you want them to do is you want them to be to return some Python code that you could just copy and paste somewhere, and it would create a copy of the class object that you're currently working with. So here, the reason my representation looks like this is because I can just copy and paste this down here, and this will give me another copy of the x variable. Another very important dunder method is this doc dunder method up here. And the doc dunder method contains the doc string of whatever the object is. So again, the doc string is the very first string that appears inside of a class or a function or any object. And if I type x dot doc like this, you'll see that this is all of the information from the doc string over here. This is exactly the same as this over here. There's a couple of \ins over here because this is just a string. We're not printing it. If I wanted to print it so that it looked the same, I could do like print x like this. And now this is being displayed nicely. And you can see it's exactly the same as this over here. So that's docstring, constructor, repr function, and all related to things that we've seen so far. This iter function down here, this iter method, again, a method is the specific name of a function, which is an attribute of a class. So the iter method right here is something new that we're going to talk about next. And in order to talk about it, we're going to have to talk about how exactly Python implements for loops. If I come back over to the notes, where we left off in the notes, you can see there's this iter and next method definition, and it's giving us a more detailed explanation about what Python does for loops. And so here, if we have a for loop like this, this is syntactic sugar for this entire thing down here. So anytime you have a for loop in Python, what that for loop is doing is it's first calling this iter function right here. The iter function is being called on whatever is to the right of your in statement. So this b value right here, this would be like your range or your list, whatever it is that you're iterating over, that's the b. That is going to have the iter function called on it. I'm going to switch back over to the terminal and we'll see what that looks like. I'm going to go on the right-hand side over here. And before using the iter function on this factorial, I'm going to use the iter function on the list class that we're already familiar with. So I do something like xs equals 1, 2, 3, like that. We have xs down here. If I type dir of xs, we can see all of the attributes of xs. Down here there is an iter attribute of xs right here. And I can do something like xs dot underscore iter like that, and this gives me this thing called a list iterator object. This is directly calling the magic method right here, the iter. It is 100% equivalent to iter of xs like that. They do the exact same thing. Whenever you have a for loop, Python has been calling this iter function on whatever it is that you're looping over. But this is literally exactly how Python implements for loops right here. We take that, the result of that iter call over here, and we put it in some variable. I'm calling it underscore iter right here. Again, the underscore, anytime in Python you see an underscore in front of a variable name, that means that you should be scared of that variable, not touch it, because this is internal to what some other person is working on. And so called this underscore iter to indicate that this is internal to Python's iteration and not something that we create or we interact with in any way. This is just the results of these things down here. And then there's an infinite while loop, and the while loop is going to, at every iteration, call the next function on the iter object. So it's calling it on the results of the iter function, this thing over here, and not on the b. And we call this next function to get the next value. This a right here, this a is equivalent to this a up here. So the for a, for whatever variable we're looping over in the container is the thing that we're calling iter on, and a is the thing that the next function is going to give us. If I come back over to Python, the interactive over here on the right-hand side, I'll press up arrow, re-get this, underscore iter equals this. So have our underscore iter variable right here. And I'm going to call the next function on underscore. First, let's just take a look at what the xs contains inside of it. And then we'll call the next function on the underscore iter like this. And you can see the very first time I call next on underscore iter, it gives me the first entry in this list. The next time that I call it, it'll give me the second entry in this list right here. The 2, I'll call it one more time, and that gives me the 3 right here. And then now there are no more entries in this list, and the way Python indicates that is this next function is going to raise the stop iteration exception. And down here in this while loop, so every time we try to do this thing right here, and then if we get the stop iteration exception, we break out of the while loop. So this code right here, this, I don't know, 6 lines or so, is 100% equivalent to just this one line up here, this single for loop. For A and B is internally Python runs this whenever you write this. If we come back over to our code and take a look at how this works with the factorial class, this iter function right here returns just it calls this constructor right here, factorial iter, and passes it in its self.in value. In general, your iter functions, your iter magic methods are always going to be just very simple things that have a return and then a call to a constructor after them. That constructor will always be for a separate class that you have created that is only like a helper class of the original class up here. And you'll notice up here that I called this class factorial. So down here, I called this class factorial iter. That's a common idiom in Python so that you know that this is the sort of like the for loop helper class for the factorial class. You just name it the name of the class and then iter at the end. Inside of this factorial iter class, there is a constructor, this right here, so the init right here. And again, the self, we don't count that as one of the variables, one of the parameters. It's just the in over here. So there's one real parameter that gets passed in, one parameter right here getting passed in, and then it initializes the class like this. I'm going to go through the code in detail here step by step in 1 second. But before I do that, on the right-hand side, I just want to repeat what we did with the list and show that those same exact procedures are going to work with the factorial. I'm going to clean up my screen a little bit, so I'll press Control D to exit out of Python back in the terminal. Let's reset that up arrow back into Python. And again, if I do something like f equals factorial of 10, so this f object is the factorial thing itself. It does not make sense to do next on f. That does not make sense. That gives you a type error. Instead, what you have to do is you have to create your iteration, the thing that you is storing the information about what you're looping over, equals iter of f like that. The iter class down here has no repr function implemented for it. So we get this sort of just generic thing down here. The factorial class, though, does have a repr function, so we get this nice looking output right here. And then in our underscore iter, we created it when we did this iter call right here. This call right here, iter of f, ran the iter dunder method of the factorial class, which ran the constructor of the factorial iter class, which ran all of this stuff down here. And so if I type dir of underscore iter like that and hit enter, we'll see that there's a bunch of these magic methods at the top, but then down here there's an I and an in and a result, which corresponds to these 3 things over here. And now if I type next of underscore iter, it'll give me one at a time all of the factorial numbers, just give me the next one, until we get to the 10th one, and it raises that stop iteration exception. The key thing about this next function, what it's doing is that it just calls the next magic method on the factorial iter class. The next magic method right here is implemented like this. Every time we run through this, it's going to increment its I value by 1, the I starting off as 0 up here. The I is supposed to represent like what iteration count are we on. and then our results multiplied by that I, and then return the results. All of the methods that you're making for your, or that we made for this factorial and factorial iter, you'll notice that they are all functions. They are all using the return statement down here and not the yield statement. I'm going to compare this code down here inside the next and the constructor to the generator, though, that we talked about, I don't know, 20 minutes or so ago now. In order to do that, I'm going to use my second tab over here. So I'll press GT to switch tabs over here. I'm going to press / to find the yield statement down here. And there we go. And I'll do the left square bracket so we can see the entirety of the generator definition right here all at once. And again, this is very simple code, just has these 4 lines down here. But we're going to compare how do these 4 lines look? What do these 4 lines look like compared to all of the code that we created up here? Up here in this init function, we have an in value here that's being passed in. This value that's being passed in is almost always going to be the same values that are being passed into your generator function. Unless you're doing something weird, it's going to be the same values that you have up here. Similarly, so we just have an in being passed in to the generator function. So in the constructor of our iterable, we just have an in being passed in right here, and then setting the self value equal to in right here. This self.result and self.I, where do they come from? They come from these 2 lines right here, that the result equals 1 right here. Result equals 1 corresponds to this self.result equals 1. And this I right here corresponds to all of the things that we're looping over in the range right here. In general, any local variable in your generator corresponds to a class attribute in your iter function. I'll write that out because that's an important thing to make sure that you understand. A local variable in your generator function corresponds to a class attribute in the iter class. And in general, in your constructor up here, you'll be initializing all of those class attributes. The constructor should initialize those attributes. And then the next function down here, the next function is going to give me the results of each of the loop iterations down here. So during the loop iteration, I have to increment the I value, get the next I value from this range, and then modify the results, and then yield the results. Over here, I get the next I value from the range, just adding 1 in this case, modify the results by multiplying by I, and then in my next function here, I will return the results instead of yielding the results. So these 3 lines of code just correspond to these 3 lines of code right here. And we've changed the yield to be a return statement. The only last thing is up here, we have to check when do we actually stop our iteration right here. When do we actually exit out of our for loop? When do we raise the stop iteration exception? And we do that in this case when our I value, the number of iterations that we've done down here, has now exceeded the maximum number of iterations that we were going to do. And this condition right here is coming from this for loop right here. How far up in that for loop am I going? There's a lot of things that I just went over. So I'm going to just do a real quick summary of everything now that we've seen all the different parts, and just hopefully that quick summary will maybe fill in some of the gaps that you missed before. So again, the big picture idea is that we use a generator we want to use a generator whenever we have a function that we're going to be looping over, because the generator will have much better memory complexity. And the generator corresponds to the yield keyword. And anytime you have a generator with the yield keyword, Python internally creates several classes for you. 2 classes. The first class will have this iter function up here, and the iter function is responsible for returning the iteration object. The top class up here, this class up here is called an iterable object. Any class that has an ITR inside of it is called an iterable class. It's something that you are able to iter, something that you are able to call the next something that you are able to call the iter function on is an iterable object. So this is an iterable object because it has the iter class right here. And then down here, this is our iteration class, or our nextable class. It's nextable because it has a next magic method inside of it that we can use. This is the thing that actually keeps track of the information from that individual for loop down here. And this is the thing down here that will have the actual code from your generator over here. The class that has the iter inside of it is the only class that needs to have any code from the generator itself. Only the iteration class and not the iterable class. The iterable class is always very simple, just storing your parameters that are passed in, your local parameters, and then calling the function down here, calling the constructor for the factorial iter. The for loop, anytime you call a for loop, it will first call that init function in order to initialize this constructor down here, create these values, and then every iteration through the for loop, it will call this next method right here to do the actual computation, to compute what is the next value that you're getting. And whatever you return right here from your next method, that's going to be the thing that comes out in your for loop. So if we do the for I in factorial I, print I equals I. Whatever we return right here, this is going to be the value in the I over here to the right of the for statement right here. Went over a lot of things pretty quickly in the last 20 minutes or so. Are there any questions at this point? Visa. So the factorial iter class does not have an iter method inside of it. And so if over here, I'll do again, so let's just restart a Python session. Oops, reset my terminal. Restart a Python session, say f equals factorial of 10. We'll do, I'll do 20 this time. And I type f. Here's my repr function being called. If I type dir of f like this, we can see that f does in fact have an iter method inside of it. If I call itr of f like this, that is equivalent to doing this. There's no difference at all between these two things. This is just a little bit more convenient to use. And then my underscore iter equals iter of f like this. And my underscore iter dir of underscore iter like this does not have an iter method inside of it. If we look through all of here, we will see there is no underscore iter, no dunder iter method. I can verify that in a number of ways. One is I can try to call the iter function on it, and you'll see that it is not iterable right here, that you can't call this on this. Similarly, you can't do that, has no attribute iter. You can only, so this factorial iter, we say this is not an iterable class. This is not an iterable class because you cannot call the iter function on it. Iterable literally means that you're able to call iter on the class. This is the result of calling iter, so it is an iteration or nextable class. It is nextable because you can call next on it. And so down here, if I do underscore iter dot next like that, that gives me the next factorial, and that's 100% equivalent to just calling the next function directly like this. So you can call next on this class. You cannot call iter on this class. On the first class, you can call iter on this class. This is iterable. This is iterable. It is not nextable because it has iter but not next. And every time you're in a for loop, anytime you're in a for loop, the iter function will be called exactly once on this original container. The iter function will be called exactly once on the container. And the next function will be called many, many times on the result of calling iter. Next function called many, many times, iter function called exactly once. Did that answer your question somewhere in there? Sort of? So I can call the iter function as many times as I want on the original factorial class. So if I did something like for I in factorial 3, and then a nested for loop for j in factorial 3, and then print I times j equals comma I times j. Whoops, I have a u. Then what's going on here is at this for statement right here, it's going to call the iter function on this object exactly once. And then it'll call the next object on to get the I many, many times. On this for statement, it will call iter exactly once on this and call the next many, many times on the j over here. Here, these are two different factorial objects because they're this is calling the constructor, and the parameters happen to be the same, but Python doesn't reuse, it doesn't know that these are going to be the same thing. And so if I really wanted to loop over the exact same factorial object, I could do something like f equals factorial of 3. And now for I in f colon, for j in f colon, print I times j, and we get the same exact things down here. This is the same exact container right here, the same exact container that's being looped over. But we have one iterable object. The factorial is the only iterable object. But we have two different nextable objects, two different factorial iters that get created because there's these two different for loops right here. And that's what keeps the I and the j separate from each other and able to keep track of things separately. This is legitimately like a very confusing thing. There's a lot of moving parts inside of here. And so if it takes you like a while to sit down and understand these things, that's 100% okay. For your homework this week, you'll have to implement two fairly simple functions. One that does instead of factorial, it does the Fibonacci sequence, and another one that does that just re-implements the range function, the standard built-in range function in Python. In both cases, you'll have to do one using the generator syntax like this, and one using the full-blown classes like this. One last thing for us to end with today. I started with this sort of talking about up here about the shibboleth, about ways that people know that you're a beginning programmer, about don't say OOP, say OOP, or object-oriented programming. Another way that people know that you're a beginning programmer or specifically not a Python programmer is by the way that you name your variables. And you'll notice that my class names right here, these are what are called camel case because these capital letters look like the humps of a camel. And all of my other functions are what we call snake case because the underscores look like snakes connecting things together. And so Python is a snake. And so in Python, all functions, whether they are methods or global functions, should be written like this. And classes are a special thing. You should think about trying to avoid using classes whenever possible because it's not snake case, it's camel case. And we are in Python and not some sort of camel programming language. If anybody has any questions about any of the technical stuff today, I'm happy to stick around and get those answered. Again, running through all of this in Python Tutor would be a good way of visualizing what's going on, that we focused on using the terminal today instead of the visual representation in Python Tutor. But that is it for today.